Welcome back, everybody. Thank you. We're going to go into a little bit of a science chat, and for those who may be streaming, I'll just mention the email question place that you can pose a question if you like. Again, the address is corrim@mmc.org. We've just swapped Dr. Sears and Dr. Zuckerman. They were really anxious that we weren't going alphabetically by their last names. So we thought we'd just flip that around. No, they'll explain kind of why, I think. But Dr. Sears, Ted Sears, is up first, and he's going to be really drilling into the newest drug that Emily was talking a bit about, Orkambi and the Kalydeco stuff. So we'll get a good dose of that. A lot of people are curious about this, and this is what we'll cover first. And then Jonathan Zuckerman is going to come up and talk about genes to dreams, but give a bit more of a contextual view of what's kind of going on in the science space. So thank you both for coming up, and I'll let you pass off directly when you're done.
Well, I'd like to thank the family group for inviting us here today. We're always excited to come talk. Jonathan and I decided to flip-flop our programs a little bit just because actually I'm going to be starting with a little bit of data about Orkambi and what the sort of next things that are coming down the pike that are sort of Orkambi and F508del related, and Jonathan's going to sort of take us out to the farthest frontiers of science and the stuff that's coming next, and so it makes a little more logical sense this way, hopefully.
Let's see if the mouse works from there.
Yeah, we can try that. So, as I said, I'm going to be talking a little bit about F508del and what's coming down the pike in terms of new therapies. Let's see if, so I do have a couple potentially relevant disclosures. I am the site PI for the SNOW 6 trial, which we will be mentioning today. As well, and I do participate in a number of other trials through the Cystic Fibrosis Foundation Therapeutic Development Network. And we are a site here in Maine. Actually, all of the doctors who you see in Maine are involved in research through the TDN. And we're really excited that Emily gave us a shout out there. We agree 100% that the future of this disease lies in the research and the new things that are coming down the pike, which are hopefully going to start having broader and broader applicability to every patient with CF. And although I am going to talk about F508del today because it's a really common mutation, we will be, a lot of this stuff is, as I said, is spreading out to everyone. So starting off with a little bit of background about F508del, why do we care about it? Why do we talk about it? It is the single most common mutation, and as Emily was alluding to earlier, this is becoming a genetic disease. As a CF doctor, the first question I ask when I meet a new patient is what's their mutation, because that really defines some of the therapies that we use already. And so F508del is at least 86% of the U.S. population thereabouts have one copy, and 47% of patients in the U.S. have two copies of F508del. And so it is sort of the gorilla in the room when we're talking about the genetics of CF. You don't need to worry too much. The reason it's called F508del is because it deletes the 508th amino acid in the protein. And for the science geeks in the room, this is how we break down how mutations work in CF. And so there's the basic classification. Obviously, everyone has DNA in the nucleus of the cell, and that's actually where the mutation lives. But how the DNA changes affect the function of the protein is really where this disease comes from. And so that we can talk about different types of mutations. This is F508del is what we call a class 2 mutation, which is to say that you have DNA gets made into RNA in the nucleus, and then it comes out. And your cell has little factories that are supposed to turn that transcript into the protein, into CFTR. And the problem with F508del is partially that the factory does not work, that when the cell tries to make the protein, it fails. And then partially that if it does somehow manage to successfully make the protein, when it gets up to the cell surface, and this is a little diagram showing the protein to the cell surface, it doesn't work very well. And so we call that a combined class 2 and class 3 mutation, which is to say there's a misfolding component and there's also a decreased function, as well as some increased turnover. So I'm going to start off with talking a little bit about Orkambi, because Orkambi is, as you guys all know, the really exciting new drug that we're using for patients with F508del who have 2 copies of the genes, so-called homozygotes, which is they have 2 copies of the same gene. And it's sort of the framework around which a lot of the new drugs coming down the pike are built. So this is actually meant to represent that process I was just talking about, where your cell is going to try and make a CFTR protein. As we're going to see here comes a little ribosome that's trying to make the protein. And as the protein is being made, we see this little purple thing coming in and binding to that protein. That is lumacaftor, which is one of the 2 drugs that's in Orkambi. And the point of lumacaftor is to help this protein fold correctly, because as we said, the problem with F508del is when your body tries to make it, it doesn't fold right. And this protein sort of fits in like a little bit of a key in a lock and forces that protein to fold more correctly than it would otherwise. So we see suddenly that sort of, and suddenly we see a completed protein suddenly being made, whereas previously the body was not able to make that protein. And then the second step is that those completed proteins need to travel across the cell from where they're made out to the surface of the cell, which is where all the action happens. And so here you can see a bunch of those proteins jumping onto the surface of the cell, which is the way they're supposed to. So lumacaftor has done the first part. Now the problem is that even if we get this in there, you can see the lumacaftor still stuck to that protein. Doesn't actually necessarily work that way, but for the graphics point of view, you can still see it's there. But you'll notice there's these little green things, and these little green things are the chloride ions. And we know that CFTR, one of its big functions is to be a chloride channel. And you'll notice there's a lot of chloride ions down here, and not very many are making it through the protein. Okay, so that's the second part of the problem with F508del mutation, is that it's a gating mutation, and it doesn't want to, the protein, even when it gets to the cell surface, doesn't want to open, it doesn't want to let those chloride ions out. So now, suddenly we see a second molecule come in. Ta-da, and that is ivacaftor. That is what is sold as Kalydeco, but is also part of Orkambi. And when the Kalydeco hits the mature protein at the cell surface, it suddenly opens it, and a lot more chloride ions can go through this protein. And so this is the correct. This is sort of the new thinking in how are we going to rescue CFTR and actually deal with the molecular basis of the disease, is cocktails of drugs. One drug that does one thing helps the protein fold. Another drug that helps open the protein. Other drugs that may have other effects down the line. And that's sort of the initial success of Orkambi is sort of really pushed forward this whole idea of how do we fix the basic defect in CF. Okay. The other thing I'll just point out, if you guys have questions as we go along, please feel free to ask them. I prefer audience participation. I'm trying to make this as clear as possible. If I lapse into science speak, please stop and be like, hey, that doesn't make any sense.
Are you going to explain why it's a problem for people with CF when those proteins don't do it this way?
Okay, I can go into that. I didn't put a couple of slides in that specifically. I was trying to keep this tight, but the real problem being that we just talked about how CFTR's job is to allow chloride ions to exit your cells in the airway, and that actually turns out to be really important for maintaining the proper amount of fluid and water in the airway and in the mucus in the airway. And when you don't allow chloride ions out, there's not enough water in that mucus. You end up with thick mucus. And then thick mucus gets infected, is hard to cough out, and over time causes damage and destruction to the lungs. And you get this sort of vicious cycle of infection and inflammation. But the root cause, we think, and there's actually still debate about this, honestly, but the current orthodoxy is that if we can open up and make CFTR work, we will loosen mucus up and make it thinner, make it easier to cough out, and decrease the amount of infection and inflammation and lung destruction that happens over time. So this is the data that we have from Orkambi, which, as I said, is lumacaftor and ivacaftor, these 2 drugs. Lumacaftor, the folding corrector, ivacaftor, opening the channel. But it really only works for patients who have 2 copies of the F508del gene. So you have to be one of these people who's a homozygote. This is data from the New England Journal article published last year, which is sort of, and you can see 2 things. Number one is the change from baseline in percent predicted FEV1 for patients who are put on our combi is pretty modest, okay? This is 0, this is 2, this is 4. So we're talking about a 2 to 3% improvement in their FEV1, which is not, it's, well, don't get me wrong, any improvement in your FEV1 is good improvement in your FEV1, but it's not, it's not knocking it out of the park, and it's not the size of improvement that we saw with ivacaftor in patients who have G551D. They got a 10% improvement on average in their lung function with the addition of ivacaftor. So this is a much more modest effect. The real benefit from our point of view, the biggest benefit from our point of view, is probably in the second graph here, which is pulmonary exacerbations in patients who are on our combi. And so here are patients who are on placebo, and the patients who were on the higher dose of lumicaftor, the twice-a-day dose, which is the dose that was actually approved and is used, had about a 60% drop in events leading to hospitalization and a 50% drop in the number of times they needed IV antibiotics. Now that's huge, right? Like that, going down from being admitted 4 times a year to being admitted twice a year makes a big difference in your quality of life. And so really, the FEV1, yeah, it's good. I'll take it. Don't get me wrong. I'll take anything I can get. But it's probably the exacerbations are the thing. But in the final analysis, this wasn't we didn't knock it out of the park here. Okay, we got a solid single or maybe a double. So this is another thing that Emily had mentioned earlier, which is sweat chloride values. Why did she taste less salt on her skin when she was on these drugs? Okay, so across the bottom here are different levels of mutation, more or less, in patients who have CF. So controls would be people who do not have CF. And they normally have a sweat chloride of about 20, okay? Patients who have one abnormal gene and one normal gene, incidental heterozygotes, occasionally have slightly elevated sweat chlorides, but it's still pretty low. There are actually people out there who actually have 2 CF mutations, but they're pretty mild. They have a sweat chloride that's in the 50s. They don't get lung disease. They don't get pancreatic disease. Actually, we find them sometimes because men don't have vas deferens, which is the tube that connects the testis to the penis. So they get found incidentally, they can't have kids, and someone, oh my gosh, he doesn't have vas deferens, they check, oh, he's got CF, except his sweat chloride's so low, he never had any symptoms. When we start getting sweat chlorides in the 60 to 80 range, we get patients with a quote-unquote milder form of CF. Those are usually patients who are pancreatic sufficient but have lung disease. And for the patients who have really high sweat chlorides, they're up at 100. They are often pancreatic insufficient patients with CF. And this is broad strokes, and your mileage may vary, and the exact sweat chloride that any individual patient has and their exact symptoms don't correlate incredibly tightly. So you don't all need to go home and check the sweat chloride results tonight.
But honestly, just to make sure I understand,
Yep.
508 is severe.
508 is severe. We'll get to that soon. But most patients with that 508 del who are homozygotes are up here in around 100 or 110 or 120. They're way, way up there. Okay, so what happens when we add our combi? As I mentioned, there we are. It's a modest improvement, right? We actually saw a negative 10, a drop of 10 in the sweat chloride with the addition of our combi. If you compare that to Kalydeco, which is the drug that Emily's on, she got a 50-point drop in her sweat chloride on average. This is pooled data. 50-point drop in sweat chloride for patients who are on Kalydeco. Okay, that, as you can see, could take someone who's in the severe range of sweat chloride and potentially bring them down into the sort of asymptomatic range. And that's sort of the cool, this is like the oh my god moment with Kalydeco. Orkambi, once again, good, definitely better than anything else. I mean, there's no drug like it out there, right? But we're just doing a totally different magnitude of effect. And so the real goal is, how do we make this bigger, right? How do we get a 20 or a 30 or a 40 for patients with F508 del as opposed to the negative 10? And there's a bunch of different areas where we're going with this. One idea that I'm going to talk about is what are called GNSO drugs. GNSO, and this is once again, dip into basic science here. Don't worry too much about the details. Is an enzyme that affects nitric oxide, and it turns out nitric oxide is a really important chemical inside the cell for all kinds of different functions. It does regulate CFTR. It also regulates how much your bronchi squeeze down, and when you have, when you're coughing and your bronchi are really squeezed down, there's some NO effect in there. And so it turns out that we can manipulate another enzyme that affects the GSNO, GSNO reductase. And these pictures down here just actually prove that there is actually a fair amount of GNSO reductase floating around inside the cells of patients with CF. It turns out that if you inhibit this GSNOR enzyme and thus increase actually the amount of GSNO, we don't need to go in there, you change CFTR maturation and you help the cell produce more CFTR, which is similar to what we're trying to do with lumacaftor, right? We're trying to help the cell produce CFTR. So right here, if you have normal GSNOR, you produce an F508del CFTR. So these are cells. These are cells. This is basic science. You're playing with cells in the lab. If you have normal amounts of GSNOR, you produce very little CFTR, which we know we're raised with F508del. If we inhibit GSNOR, we start to see some amounts of immature and mature CFTR being produced. So this strategy of trying to inhibit this enzyme does seem to help the cell produce more CFTR totally differently than lumacaftor does.
Where is this research going on, and is this U.S. or UK or?
So we'll talk about this. This actually, a lot of this stuff is that we're coming to sort of where the trial, there's actually an ongoing trial here in the U.S. Here in Maine Medical Center of a drug that does this, and that's one of the reasons I'm talking about it, because it's in phase 2, and we are enrolling patients right now to try this drug. GNSOR seems to also increases cell surface CFTR. So not only does the cell produce more of the protein, but it actually gets to the cell surface. Not as dramatic, I'll be honest, and you don't need to get into the total details here, but N1975 is a drug like lumacaftor, which helps the cells make CFTR. And if you give them nothing, they don't make much CFTR. If you give them a corrector, they make more. But if you give them the corrector and something that inhibits this GSNOR enzyme, it makes even more. So it seems to add on, GNSOR seems to add on or boost the effect of correctors by a different mechanism. This is N9115 is actually a candidate drug, a molecule that's in development, and as I said, in current clinical trials. And this is what we think it does inside the cell. We think that you don't need to worry about the little H's, but the one thing it does is it decreases the amount of CFTR degradation, which is to say, increases the amount of CFTR being produced in the cell. There's another corrector that binds and helps the folding. It gets to the cell surface, and then once it gets to the surface, it turns out that, which I didn't really get into, but it also appears that N9115 and this GSNOR reductase helps stabilize the stuff at the cell surface, stabilize the CFTR, and decrease the degradation of it. And so that you have the potential to rescue more CFTR, get it to the cell surface, have it stay at the cell surface longer. All of which you would think would boost the effect of corrector molecules, boost the effect of drugs like Orkambi. So, actually, and as I mentioned, I am actually the site PI for this study. We are currently trialing this drug with the goal of seeing if you add this to patients who are already on Orkambi, does the Orkambi work better? Do they get a bigger benefit from Orkambi by adding a booster drug, more or less, to it? We are, so this is a phase 2 trial. We're really looking at safety still. We are starting to look at effects on lung function. We've actually, we are enrolling patients right now across the nation into this trial, and we'll see. We don't know the answer. It works great in a test tube. I've shown you some basic test tube data. The real question is, what happens when you start giving it to patients, and that's what we're trying to find out right now.
Might it be pill or inhaled or?
Currently, this is a pill. Currently, this is a daily pill. And
can you talk about Nivalis just?
So Nivalis is the company that is developing this. So they are one of the drug companies that's working closely with the TDN, and this is their candidate drug. So they are funding the trial and eventually they hold the patent on this drug, and they eventually hope that if it works, that they'll be able to sell it. Okay, so that's one arena. Other ways that we're looking at improving things going forward. VX661 is you might want to think about it as sort of the next generation of lumacaftor. It is another drug that works very similarly. It helps folding in the cell, as we saw. It has fewer drug-drug interactions. It has a longer half-life. And there is phase 2 data, that's already been studied, where it did seem to help patients with F508del. So these were actually mostly homozygotes. Don't worry about the heterozygotes with the gating mutations, but there was this is FEV change in FEV1% predicted, and you'll notice, at higher doses, we're not just talking about 3-4%. We're talking maybe 7%, 9%. This may be a slightly better drug from an FEV1 point of view. We don't know yet, but it certainly doesn't seem to hurt, and it may have some benefits to making to dosing and fewer drug interactions, et cetera, et cetera, et cetera. And there's actually some interesting test tube data once again about the potential that lumacaftor and ivacaftor, although they both seem that we think of them as helping each other, they may not entirely help each other, and there's a possibility that they're actually having negative effects on each other, and that VX661 in place of lumacaftor may work better because it just doesn't. There's not any interference between these two drugs. So there are actually multiple phase 3 trials going on of VX661 and ivacaftor. So the next generation of Orkambi that are in various combinations of patients with, but homozygotes, patients who are heterozygotes who have specific types of mutations, and patients who have heterozygotes without these other specific types of mutation. These are all phase 3 trials. We expect data from them in the next 6 months to a year. It is quite possible that we'll have a second generation of Orkambi coming out in the next year that may work better. Really exciting. We don't know yet. Stay tuned.
Would the second generation of Orkambi replace the first generation?
Well, that's another big question. I think the real question is going to be how do these two compare in actual real world use? Are there other side effects that we find out that come in? At least it'll give us another option. And so that there'll be the possibility of having Orkambi and a different drug. And if you didn't do well with Orkambi, maybe you'll do better with another drug. We don't know the answer to that, and I would think up front the likelihood is that they'll both be available, but who knows? Is this going to replace Orkambi? We don't have the data yet. Other questions?
I have another question.
Yep.
At what point, if any, is the sweat chloride retested after starting Orkambi?
So we don't act. Oh yes, repeat the question. So the question was, at what point do we retest sweat chloride after starting Orkambi? And actually, in clinical practice, we do not. Sweat chloride measurement is really a research tool. It proves the diagnosis of CF when you have a child who does this baby have CF or not. Doing a sweat chloride will help you. In terms of actually using it in clinical practice to make decisions about how we treat patients, that is not done. And so everyone who gets started on Orkambi, either they take the Orkambi and they do well with it, or they take the Orkambi and they have side effects and they have to stop it. But we don't check their sweat chloride after they start it in general. Okay.
One quick
Yeah.
one. Do you know if either of the two tracks you've just discussed are similarly being co-funded by the CF Foundation and these drug companies with sort of rights the same way? Sort of, the CF Foundation was brilliant in terms of sort of selling future rights
Yep.
to Orkambi and Kalydeco and
Yep.
making over $1 billion.
Yep.
I'm curious about this one
Yeah.
and others. Is it a similar model or not?
Well, and it depends a lot on the specifics of the specific issue, and I don't know. I can't answer. In general, the CF Foundation has done a fantastic job of partnering with industry. But in terms of who exactly holds what percentage of the rights to each of these compounds, that I'm not able to answer that question. Okay. So last thing I'm going to mention are VX152 and VX40. I'm going to try and move fast because I'm almost out of time. These are other corrector molecules that may help improve the effectiveness, once again, of either a VX661 or potentially Orkambi. In preclinical trials, triple combo therapy, where you took a 3-drug cocktail as opposed to a 2-drug cocktail, worked about 3 times better than Orkambi in terms of chloride flux. And so this would be a change in sweat chloride of about 30, which once again may be more significant. So once again, here's triple therapy, and here's Kalydeco. Suddenly, we're not just doing 10; we're doing 30. We're starting to see bigger effects clinically, and that's the hope. When we start to deal with drugs that do a better job of correcting, we'll get better changes in sweat chloride. We don't know. There are phase 2 trials planned later this year of these drugs. We will see whether they work well in phase 2 trials, whether they have side effects, et cetera, et cetera, et cetera. It's too early to know, but that stuff is coming down the pike and are actively being planned. So, my conclusion, the second generation a corrector VX661 is in phase 3 trials. We're hoping it's going to improve slightly on lumacaftor. The third generation of triple therapy may dramatically improve F508 del rescue. There are other things like GSNOR drugs, which may boost Orkambi in other ways. So there's a lot of exciting stuff coming down the pike in the next year, 2 years, that we're actively studying right now. And once again, this plug that when you're able, we love getting people involved in research, because this is how we move the thing forward, and we couldn't move this field forward without the patients who are willing to do research and help us figure out whether these things work or not. And I think that is pretty much what I had.
Awesome. Thank you, Ted. Do you want to introduce your colleague?
I will introduce my colleague. So I'd like to introduce Dr. Zuckerman, who is the senior adult CF doctor. I'm the junior adult CF doctor. He's been here for 15 years, and he's the director of the adult program at Maine Medical Center, and my mentor, Dr. Jonathan Zuckerman.
All right, well, I'm going to be going on a little bit of a meandering talk today. I've actually been ruminating quite a bit about how we cover. There's so much going on in CF right now in terms of basic research, and I think Ted did a great job of covering the next few steps from the development of Orkambi for molecular therapies for CF. But some people in the audience may be wondering, about what's happened to gene therapy. Is there any role for stem cell biology? And then something that I've become increasingly interested in the care of CF patients is personalized care. So we're actually going to go away from science a little bit towards the end of the talk, and I'm hoping that that's successful. All right, let's see. Okay, so disclosures. I have been working on some projects with Vertex and Anthera, and I'm on the scientific advisory board for Gilead, but full disclosure is that I'm hoping that you're going to grow in your interest with respect to our new approaches for CF care. So this is one of my favorite slides. Many years ago, we had Beth Suffian come to speak to us by webcast. How many people in the room know who Beth Suffian is? That's great. So she's pretty famous. She's a person with CF who's a lawyer. She works for the foundation and helps a lot of adults navigate through the difficulties of getting disability, having their insurance issues straightened out. And what she showed us is that when she was a kid, her treatment for CF was up in the upper left-hand corner. It's just a cup of tea, lemon, and honey. And we've come so far since that time. Now we have all sorts of therapies that we've tried to standardize in some respect over here. And then, as Emily eloquently described, the blue lightning pill that we have now down at the bottom. I think for most patients with CF, they envision a future where maybe you only need to take pills and not do any inhaler therapies, or perhaps have a one-time cure. So that's always something that's on our radar screen. So right now, why do we standardize care? This is an issue that doesn't just affect CF patients. It really cuts across medicine in the United States overall. But it allows us ways to improve the care of patients by raising at least the general standard of what's provided to people. It improves efficiency. It gives the healthcare team a convenient framework around which to think about care, and it may make our care more uniform across healthcare systems. So along the lines of standardized care, we also have guidelines, and the CF Foundation has been very proactive in developing guidelines. Can everybody hear me okay? No. Stay near the mic. The guidelines have helped us with respect to respiratory care, nutrition, exercise, and social work. The problem is, and how many people have read about the sneeches? Something that is in style at one point may fall out of style at another point. So sometimes what we have that happens with standardized care. It's our best approximation of what should be done, but then 5 years later we find that maybe we were a little bit off target. And how many people have heard about vitamin D? It's in, it's out, cholesterol in and out. So we have to be aware that just because you're getting standardized care doesn't necessarily mean you're getting the best care. Our goal in implementing care in a standardized way is that it should be intentional, not just an assembly line. And we're going to get back to that a little bit more later. Evidence-based medicine is a conscientious, explicit, and judicious use of current best evidence in making decisions about the care of individual patients. And that's a really tricky thing for healthcare teams to do, to think about the individual. Sometimes things have to be custom fit. Now, last year I was very excited. I gave grand rounds at Maine Medical Center, and I think it was the day before my talk, Barack Obama gave a State of the Union address, and he had actually a CF patient stand up. Does anybody remember that talk? Yeah, I thought that this was brilliant. I was very excited to hear him talk about a term he called precision medicine. And in the final sentence, he said, in some patients with cystic fibrosis, this approach has reversed a disease once thought unstoppable. And I thought a little bit about the notion of precision medicine. I actually like the term personalized medicine a lot more. And we're going to touch on that. Dr. Sears was really touching on precision medicine that's largely grounded in the study of genetic mutations. And so we're trying to customize treatments to people who have various genetic predispositions to disease. Personalized medicine is different. And just think about that while I go through the rest of the talk. I'm going to come back and tell you what I think personalized medicine is a little bit later. But before we do that, I'm actually going to launch us into some what seems like science fiction here for a little bit. We're going to talk about gene therapy and stem cell biology for a little bit. Okay, so the story begins back in 1989. This is when I was still doing my medical residency. I didn't even really think much about CF at that time. But the gene was cloned in 1989, and the abnormality is found on the long arm of chromosome 7, and the protein that Dr. Sears was talking about, the CFTR protein, is a protein that we for many years have thought about as inserting into the lining cells of many of the organs in our body. So the airway lining cells, the lining cells in our GI tract, the reproductive tract. I'm going to give you some surprises in a few minutes, but for the most part, we have thought of the CFTR protein residing in the tippity top of these airway lining cells. That's where the major problem is. And these beautiful green projections are the cilia, which move mucus up the airways. So we think that CFTR is mainly doing its work along this red stripe that's called the terminal bar. Now, the three major labs that were involved in the discovery of this gene actually crossed boundaries between the United States and Canada. Dr. Francis Collins, who's become quite a bit of a rock star himself at the CF Foundation, is now the head of NIH, and he was the lead scientist on the Human Genome Project. For those of you who've heard about the Human Genome Project, he was part of the governmental research team for that. He was a co-discoverer of the CF gene, and I see him as somewhat of a prophet, seeing where the field of medicine is going in CF. Now, shortly after this team discovered the CF gene, I was working at the University of Pennsylvania, and we were working on gene therapy. Everybody at that time thought that gene therapy was going to be the cure for CF, and the head of our lab had a very simplistic view of how to fix the problem. He said, I don't really care what CFTR does. We know that this is a recessive disease. What that means is if you just correct one copy of the gene in the cells, you've corrected the problem. So you don't have to understand the biology. If you could just get that blasted gene in, it should work. And actually in the test tube, it works great. We had no problems getting transfecting cells. At that time, we were using adenovirus, and we would cure the CF problem in these test tube cells. The problem is our body is designed to reject foreign invaders, foreign DNA. That's why we fight viruses, viral infections. You may fool me once, right? But after I'm vaccinated or infected, I don't get infected with the same virus again. So we actually had to take a big step back. This is back in the early 1990s, just to give you a little bit of a time frame. Almost 20 years ago, actually it was the mid-1990s, that we found that gene therapy was not working the way we had designed it. We had to go back to the drawing board and understand what's actually going on in the cells. And I've actually updated this slide since I last showed it at Maine Medical Center. What I had down here was we had to learn more about airway biology. And now I'm realizing we have to learn more about cell biology in general. Because as it turns out, we just covered this in our journal club a week or so ago, it looks like CFTR is not only expressed in the airway lining cells, it's actually also expressed in the muscle cells that line the airway. And so people with asthma, they get bronchospasm because the muscles contract. We now know that CFTR is expressed in the muscle cells of the airway. And that may be one of the reasons why when we give a medicine like Kalydeco, there's an almost immediate response, much faster than you'd expect if somebody just had lots of mucus and airway remodeling with scar tissue. There's actually some bronchospasm. So that I thought was a fascinating thing. We're learning more about the biology of this disease every year. Now, how much CFTR function is enough? I'm going to blow through this slide quickly because Dr. Sears kind of covered it nicely in his talk. But basically, we realize that we don't have to correct all of the CFTR dysfunction. Somebody who has about half of the wild type amount of CFTR function, for all intents and purposes, looks normal. So our strategies don't have to get you up to 100%, but we think that in patients with G551D, we're getting about 50% correction, and we probably don't even need that much for people to really notice a difference with other mutations. Now, one of the things that I thought was so inspiring at the CF Foundation, I think it would be pretty easy to say, you know what, we've gotten a couple of good products here. We're going to focus on the people who have the mutations that are most frequent. You know, F508del, we want to do a lot of work on that. The problem is there are about 2,000 mutations that have been identified that cause CF, and some of them are very, very rare. And some of them are so rare that you'd never be able to do scientifically adequate clinical trials with placebo and drug in enough patients to get valid results. So you could just hang up your shoes and say, you know what, we'll just do standard therapy for those people that we talked about. Standard therapy is pretty effective, but the CF Foundation actually is more visionary than that. And I'm very impressed that they feel, as part of one of their mission statements, they want to try to find a treatment for every patient with CF. And some of these may be tough nuts to crack, but they're not giving up on it. And one of the ways, and I'm going to actually, in the interest of time, go through these slides very quickly. We should be able to have these things up on the web at some point so that people can look them over. But if you notice these different colored circles, these are trying to indicate graphically the percentage of patients with different types of mutations. So there are different strategies being taken for different types of mutations. And notice as we get to the end, the whole grid is filled with different strategies to treat different mutations. And so that's all the more reason for all of the patients, well, we don't have too many patients in here, but families and patients to know what the genotype is. Okay, that's kind of like Social Security number. You want to know your genotype because there may be clinical trials that are targeting certain types of mutations, certain specific mutations, or certain types of mutations, and it's in your best interest to know what they are and what they mean. There is a website, the Johns Hopkins CFTR2 website, which is actually constructed not only for doctors and researchers, but also for patients and families. There's a patient and family side to that. So if you just type in CFTR2, do a Google search, you'll find this. And this is just an example of how it would walk you through. You put in your the designation, and it gives you a kind of a review of what's out there, how do patients generally do with the mutation, and what type of mutation it is. Now, there are going to be some rare mutations that aren't even well described in CFTR2. And then we still want to try to come up with strategies for treatment. And if you look at this slide here, it has some little mini movies here. Did you notice that the cell on this side is growing? It's swelling. Well, one of the things that Dr. Sears was talking about is CFTR, one of its major functions is it controls the movement of salt and water. And when you get salt and water moving into a cell, it blows up like a balloon. So this is showing activation of wild-type CFTR with a CFTR activator called forskolin. And here is a cell, a similar cell, with the CF defect. And you can see that it doesn't swell. Now, wouldn't it be interesting if we could harvest some cells from a patient and test a battery of different compounds rather than subjecting them to pills that they might take for several months and wonder, is this working or not working? Because as you know, there's always a chance that you don't have an exacerbation anyway, whether you're on the med or not. So you'd like to know, is this medication actually affecting the mutation that we're interested in? And so this is a line of research using intestinal organospheres. Basically, they can harvest some cells from the patient's body, grow them up in a petri dish, and then test a range of different compounds. So once we have a portfolio of compounds that are available, we can customize it to the patient. Very exciting. This is another way of looking at it. These are these organoids, and you can see that there's a stepladder of response, and it seems to be very specific to CFTR, because here we can see adding different compounds, we get an increase in response, and then if we give a CFTR inhibitor, it blocks it. So we can test in these in vitro systems. So we can take cells from the patient or cell lines that are grown up with the same mutation as the patient and test these compounds ex vivo before subjecting the person to the medication. So we've talked a lot today about treatment with these molecular modifiers. And where we're getting at treatment for these people, standardized care is continuous therapy. And Emily can tell you more about that than I can, but it's not just taking a pill. For most people, it's 2 to 3 hours a day. Okay, so that's very burdensome. Now we're moving towards daily therapy with pills, with the protein translation treatment. Those are medications like Kalydeco or Orkambi. And then you start getting into more futuristic looks at actually trying to repair the genetic underpinnings of the disease. So these would be looking at permanent repairs or periodic treatments with genetic therapies that might be more effective than what we were seeing in the 1990s. And here's the problem that we ran into in the 1990s. I'm just going to recap this. Most of the genetic therapy was done with adenoviruses, which are like cold viruses that would carry a normal copy of the CFTR. We were giving the virus through a bronchoscope into the lung. We were spraying it in and then trying to see how long the cells survive. The problem is that the lining cells of the lung slough off periodically, so that you had to keep redosing the medicine. And our bodies don't like to see adenovirus, so the second time you give it, there would be antibodies that would inactivate the virus. So these are some of the big problems, is that the half-life is very short, and our bodies build up an immune response. What came out this past year in Lancet Respiratory Medicine is a different strategy using something called liposomes. These are naked pieces of DNA that are in little loops, and they're held in a fat globule. That's what a liposome is. And they would spray that into the patients. And now we're starting to see, this is a similar graph to what you may have seen at other CF education days, where we're looking at changes in predicted FEV1. And again, like Dr. Sears would say, this is by no means is this a home run. I would say this is a bunt single. But you're seeing that in the placebo-treated group, there's a drop in lung function, and there's a stabilization, maybe a slight rise at times with the liposomal treatment. But what's kind of exciting here is we're actually seeing expression of wild-type CFTR in cells that are harvested from the patients. And this is a Herculean task to do this study. It was an international study that had a paragraph worth of investigators on the paper. So what's even more futuristic is actually looking at stem cells. And in our household, it seems like the answer to every question is, oh, do it with a laser. You know, so lasers are cool, stem cells are cool, I guess. But it isn't actually so far-fetched that stem cells might be used at some point to treat CF. And what the strategy that's being looked at by a lot of scientific groups currently is to actually take mature cells from the host, so take some skin cells, and actually revert them back to pluripotent cells that can then be differentiated again into whether you want it to be a lung cell or a bowel cell. And those things can actually be done now in the laboratory. They're being done on mice. There are some very exciting, and I hate to say that I get some of my information about CF by reading Popular Science, but there was actually an article in Popular Science looking at this CRISPR technique that is fascinating. It all started by studying bacteria and finding that these bacteria had incredible systems for using a scissor-like molecular system to just clip out pieces of DNA and insert them in other areas. So we now have molecular scissors to cut out a normal CFTR and splice it in to the chromosome of somebody who's deficient. So proof of principle, we can now do it. It's now ramping it up to animal models and humans. But that's something to think about in the future. And here's an example of doing this regenerative lung biology in mice. And so as long as you have the scaffolding appropriately designed to accept these stem cells, the stem cells will actually grow into new lung tissue with the air sacs and everything else. It's amazing. Now, does the CF Foundation care about this? You know, we've been hearing a lot about these molecular techniques, but I just want to assure everybody that some of this money that Ted was just talking about that's come into the CF Foundation is being reinvested into some of these long-term goals to try to get long-term, one-time cures for CF. So there are grants available for looking at CFTR gene replacement and repair technologies. There's another one looking at research tools and therapeutics, and a stem cell application through the CF Foundation. So you're bringing in some of the smartest scientists around the country who are interested in doing stem cell biology. They're actually being welcomed into the basic research community in CF. Very exciting. All right. Now, I told you at the beginning of the talk about personalized care. What's the difference between precision care and personalized care? And I spent most of my talk talking about precision care, trying to do targeted treatment to genetic defects. But I think our job as CF care teams is much bigger than that. That's one of the reasons I left the lab to go to work with patients, is that I like being at the bedside and I like knowing the people or getting to know the people that I'm taking care of. So personalized care, I think beyond just finding the right medication, is looking at some of these other things. It's trying to reduce the fragmentation of care so that the medical record makes sense to more people. It's minimizing the length of time in the hospital. It's bringing in people with unique talents so that we have a multidisciplinary care. It's not just doctor, nurse, and patient, but we have a whole team. It's continually reassessing the quality of life, establishing the goals of care, and then respecting individual choice. We have some people, for religious reasons or whatever, who don't want some of the stuff. And we need to know them well enough to know when to back off. So here's my one, I guess my second cartoon. So some of you may not be able to see this, but this is Calvin and Hobbes, and Calvin says, "I'm at peace with the world, I'm completely serene." And Hobbes says, "Why is that?" "I've discovered my purpose in life. I know why I was put here and why everything exists." "Oh, really?" "Yes, I'm here so everybody can do what I want." "It's nice to have cleared that up," says Hobbes. And then Calvin says, "Once everyone accepts it, they'll be serene too." So on a more serene note, this is my most daring slide here. I was thinking sometimes we can get inspired, certainly I get inspired by looking around in nature and seeing how can we learn deeper lessons about how we live our life, or a deeper understanding of what really is meaningful in life. And you know, when you look at a substance, if you look at gold or you look at silver or coal, the smallest unit, the smallest individual unit within that substance is a what? This is a quiz. It's an atom, right? So we think of the smallest piece of a substance being an atom. But actually, if you look at an atom, and so if we look in society, the smallest unit in society is a what? A person. So if we just look at one aspect of a person, just that they're a body that has chemicals, and then we need to fix the chemicals, we may be missing a deeper truth. Same thing in an atom. An atom is actually, if you look on a periodic table, for those of you who took some chemistry, what describes an atom, we've got some different parts here. You got the proton in there. The protons actually describe what the atom is going to look like when it's in a big clump. So you've got either gold or coal has a certain number of protons in it. But an atom is not just protons. It's got neutrons in it too, right? So if you look around the room, we've got different people. They look different. All right, we got Mother Teresa, we got Arnold Schwarzenegger. They look different on the outside, and they're characterized by their body types. But if we want to treat them more holistically, let's think of if you add extra neutrons to an atom, what happens to it? It becomes radioactive, it becomes unstable. So I think of that like the mental state of somebody. So we have the body, and then you've got the mental state of somebody. And if they're not mentally, they may look the same on the outside, but on the inside, they're really hurting. And so our complete personalized care should really address the mental state of the patient. And the CF Foundation actually put out a grant to support mental health care in adult patients. And we scrambled to apply for that, and we were very happy that we got that grant. So I don't know, if Meg, if you want to wave, but Meg is going to be our mental health coordinator. So I see that that's a critical thing. We can prescribe whatever we want. If the person is completely depressed, they're not going to take it. The third piece, which is probably even a little bit more controversial here, is that the outer part of the atom is the electron. That's the part that you almost don't pay attention to because the electron doesn't weigh anything, or weighs very little. But it allows atoms to combine. That's how they form molecules, is through the electron cloud. And so for us, I call this the spirit. If our spiritual foundation is kind of messed up and we're not connecting with other people, it's easy to get really isolated. And CF is one of the most isolating diseases there is because of infection control. People can feel very alone. So if we're not addressing the spiritual needs of our patients, again, we're not providing true personalized care. So now this is a little bit of a stretch, but social work, I think, really is a key part of that, particularly for adults when they're going through marriage, when they're going through facing a transplant, when they're going through perhaps end-of-life decision-making. Having a social worker and a palliative care specialist is critically important, and we applied for monies to help with social work, and I'm very happy to say that we're finally getting approaching the amount of FTE or dedicated time for social work on our teams to address these things. Okay, so how are we going to address the three key aspects of personhood that I think that are critically important for personalized care? We want to stay on the cutting edge of medical therapy for CF and participate in clinical trials so that people in Maine know that we're getting the very best of standardized care and opportunities to participate in finding the curative approaches to this disease. We want to initiate mental health screening program and develop resources for treatment. And these are all kind of visionary things, but we're on the launch pad right now to do that. And then thirdly, we want to work to meet the emotional and spiritual needs of our patients and families. And again, it's a big, we're setting big goals here, but I think we're on the launching pad. So I'd like to thank, this was going to be kind of a where are we going with CF research. CF research actually involves our clinical teams. You can see our clinical teams are growing, and the adult team used to be about that big for a long time. It's really the adult team is really growing. And then on the research side, we have, actually, you probably don't know so many people are involved in clinical research. So if you have a clinical research appointment, show up because there are a lot of people involved in this. But we have the buy-in from folks at the Maine Medical Center Research Institute. I knew I was going to forget somebody, but our colleagues up in Bangor, Erica Parker, has been really helpful for recruiting patients, and we're now starting to get patients from Bangor participating in our clinical research. That is a huge hit with the CF Foundation, I should tell you. It's not only important for us to know that our research opportunities are available to everybody in Maine, but it actually resonates down at the foundation in Washington because they don't like to think that there are people out in rural areas who don't have access. 2 websites that you would want to check out to learn about opportunities for research, and also I would love to load up some of these exercise videos. We're actually trying to get some video. We actually have some video content on the website, but we want to enhance that. So there's the Northern New England .org website, and then there's the CF Family Advisory Board website. So with that, I'm going to open up to questions. I think I might have run over a little bit, but thank you very much. Appreciate it.